The study of the way people make decisions, or perhaps how they ought to make decisions, is as old as the history of mankind. Thus, it is not surprising to see that the literature in decision-making is actually humongous and it continues to increase with time. On the other hand, however, the development of the perfect decision-making method still remains to be an elusive goal. So, this contradiction between the extensiveness of the study on the subject and the elusiveness of this final goal constitutes, in a way, the ultimate decision-making paradox. Today, we will be discussing a very well-known discipline in decision-making and also a very well-researched discipline in decision-making, referred to as multiple criteria decision-making. Multiple criteria decision-making, or MCDM, is a complex tool that refers to making decisions by evaluating multiple criteria, which usually are conflicting in nature. MCDM methods are used in business and in engineering settings, but also they're used in everyday life problems. Different MCDM methods, while they differ of course, still share in common certain aspects. First of which being the set of alternatives, which is denoted by X. This set is either finite or infinite. It is finite in the case of selection and assessment problems, and it is infinite in the case of design problems. Next, we have the set of criteria, which represent actually the different perspectives and the different angles from which we will be looking at and assessing these alternatives. Next, we have the outcome of each choice. The outcome is bound by the weight of the criteria which we chose earlier. And we have the preference structures of the decision maker, which actually will tell us how difficult or how easy this problem is going to be.
Our first method is going to be analytic hierarchical process, which is one of the oldest MCDM methods that dates back to 1988. AHP at its core heavily relies on pairwise comparisons to actually simplify and break down complex decision-making problems into simpler and easier parts. What it actually does is that it divides those problems into a set of hierarchies, and those hierarchies have the shape of a weighted tree, as we can see in the adjacent figure. What we do is we place the goal of the decision-making problem at the root of this tree, and the different criteria and alternatives that we'll be carrying the study on will be placed at lower levels in this tree. What's special about the structure is that each branch has a weight, and this weight actually means something. It quantifies the impact of each criterion on the ultimate goal. So what we do in this study is we try to use some statistical and mathematical methods to somehow combine all those weighted criteria and find some sort of hidden interrelationships that exist between them. Now, the aim behind this model is to finally compile a list of ranked alternatives and choose the one that best fits our ultimate goal. To develop this model, there's a set of steps that we actually need to follow. So in step 1, we'll start by constructing the hierarchical tree that we've discussed in the previous slide. So we'll define the goal of the decision-making problem, the set of criteria that we'll be using, and the alternatives that we'll be choosing from. Then what we do is we'll combine those criteria in pairs and assign something called the relative importance value for each criteria pair. Now I'm gonna explain what I mean by this value using an example. So let's say there's a decision maker that's trying to choose the best phone from a set of alternatives, and he's taking into consideration just two criteria, which are the speed, for example, and the camera, for example. So based on his preferences, the speed is much more important than the camera. And this can actually be described by a factor, which is the relative importance value. So based on his preferences, the speed is 5 times more important than the camera. So after assigning those values, we insert them into a pairwise comparison matrix. And what we do next is we normalize this matrix. So basically normalizing a matrix enforces regularity among all its elements, and in case any bias exists in our data, it would be ruled out by just normalizing it. Then what we do is we calculate the weight for each criteria, and this can easily be done by just calculating the average of each row in our matrix. So it can be done as follows. To calculate the weight of criteria I, we'll just do the summation of the elements in this row, and we'll divide by the number of criteria that we have in our study. So here the summation would be from j equal 1 to n. And that's how we calculate the weight for each criteria in our model. In step 5, we extract the largest eigenvector, denoted by lambda max, from the pairwise comparison matrix, and then we use it to compute the consistency index as follows. To assess the choice of the pairwise criteria, we calculate something called the consistency ratio. In this ratio, we compare the consistency of our data to its randomness. If this ratio yields a value that is greater than 0.1, then we should reassess our pairwise comparison matrix until reaching a value which is less than or equal to 0.1. What I mean by reassessing the pairwise comparison matrix is jumping back to step 2 and reassigning values or reassigning relative importance values for each criteria pair. So we keep iterating back and forth until attaining this desirable consistency ratio value. So now, after attaining this value, we can safely choose the best alternative among a set of options. And this can be done by calculating the AHP score. So we can simply do that by multiplying the weight of each criteria with the value of each element in each row and applying the summation of this operation to obtain an AHP score for each alternative in our study. Then what we do is we choose the maximum, the one with the alternative with the maximum AHP score, and this will be our best alternative.
Our next method is the best worst method, or BWM for short, which is actually a newer method. It was proposed in 2015. BWM, just like AHP, is a pairwise comparison-based MCDM method. It came as a remedy to the recurring inconsistencies found in pairwise comparison matrices, which are common in MCDM methods. The authors of the original paper which proposed BWM suggest that the source of these inconsistencies is actually the unstructured method comparisons are carried out by. BWM is often compared to other MCDM methods, namely AHP, where it has been able to demonstrate a lot of salient features. First of all, BWM requires less comparisons than AHP since it is vector-based and AHP is actually matrix-based. BWM also results in more consistent comparisons, and it is easier to integrate with other MCDM methods. So, how do we actually implement this method? We start off by choosing a set of decision criteria, C1 through Cn, which actually reflect the preferences of the decision maker. So for example, if I'm looking to buy a car, my decision criteria could be the cost, the fuel consumption, and for example, the actual performance of the car. After that, I'm gonna identify the best and the worst criteria. So what do I mean by that? Quite simply, the best criterion is actually the criterion that is the most desirable one for me, the one that actually means the most, and the worst criterion is the one that means the least for me. So for example, the performance could be my best criterion, and the fuel could be my worst criterion. After that, I'm going to determine the BO vector, or the best to others vector, which is actually on a 9-point scale, where 1 means that the criterion at hand means just as much as the best criterion. So it is as important as this criterion. And on the other end of the spectrum, 9 means that the best criterion is actually extremely more important than the criterion at hand. AB1 here actually references the preference of the criterion B, the best criterion, over criterion 1. So quite naturally, ABB would be equal to 1. Next, I'm going to do a very similar task, which is determining the others to worst vector. It is also on a 9-point scale, and A1W here refers to the preference of criterion 1 over the worst criterion, and also AWW would be equal to 1. So our next steps are as follows. In step 5, we want to determine the optimal weights of the different criteria we chose earlier. These weights are denoted by W1 star, W2 star, through Wn star. And we determine another parameter called zeta star, which we will be using later on in step 7 to determine a parameter called the consistency ratio. So how do we actually determine these values? What we do is that we formulate a maximum problem and we solve it to end up with these values. In the next step, we've reached the end of our method. We want to select the best alternative among the pool of given alternatives. So what we do is that we aggregate the weights, or the optimal weights we calculated in step 5 to reach this best alternative. Next, we want to actually determine how consistent the comparisons we carried out before were. So we calculate a parameter which will indicate this for us, which is the consistency ratio. We would want to see in an optimal case a consistency ratio equals to 0, because that means that our comparisons were actually very consistent. To calculate this ratio, what we do is that we divide zeta star, which we determined earlier, over the consistency index, which is the maximum value of zeta for each of the 9 scale points we were talking about earlier. So as we can see here, if we have a higher value of zeta star, we would have a higher value of the consistency ratio, and thus a less consistent comparison. So we would want to see a very small value of zeta star.
And now we'll talk about the technique for order preference by similarity to ideal solution, which stands short for Topsys, and it's one of the methods that is widely used in the literature. Topsys is an MCDM method that bases its decision-making process on Euclidean distances that are actually calculated between alternatives and optimal solutions. Now, optimal solutions can be of 2 classes, the ideal best and the ideal worst solutions. And those can actually be derived from the criteria that we have chosen earlier to carry out our study on. So what we do in this method is we try to find the alternative that has the farthest distance to the ideal worst solution and the closest one to the ideal best. Thus, we end up having a list of alternatives that are ordered based on the relative distances that we have computed using the Euclidean method. To develop this model, we'll start by constructing our decision matrix, which actually contains the criteria with their corresponding values, as we have done in the previous methods. And each element in our decision matrix will be denoted by Rij. Then we'll normalize this matrix, but the thing is that we'll not normalize it using the traditional way of just dividing each element with with the summation of its corresponding column. However, we'll use this formula to normalize our elements. In step 2, what we do is we define weights for each of the chosen criteria based on the decision maker's preferences. And those weights will be denoted by W1, W2 until Wn. So those weights will actually be used to determine the ideal best and ideal worst solutions in step 3. After determining the ideal best and ideal worst solutions, we jump to step number 4 to calculate the separation measure, which actually quantifies the distance that separates each alternative from the optimal solutions. And this can actually be done using the Euclidean method. Let's take an example where we have an ideal best solution at this position and an ideal worst solution at that position, and we have an alternative. So what we're trying to do in this step is we're trying to calculate the distance that separates this alternative from the ideal best solution, and this value will be denoted by Si plus, and the distance that separates this alternative from the ideal worst solution as well, and this value will be denoted by Si minus. Then we'll use those computed values to determine the relative closeness measure, which is actually denoted by Ci. Now, what we're trying to demonstrate in this ratio is that any alternative that has the farthest distance or the largest distance to the ideal worst solution will definitely have the closest distance to the ideal best solution. So definitely higher Ci values are desired. Finally, what we do is we rank the alternatives that we have based on the computed Ci value, and we'll definitely choose the one that has the highest Ci value, which will be the best alternative.
Now we will discuss a couple of case studies to really showcase how these MCDM methods we were discussing earlier are actually used for different problems and in different settings. Our first case study is going to be about operating system selection for firms. Okay. Our case study actually deals with a journal paper titled Operating System Selection Using Fuzzy AHP and Topsys Methods. This paper proposed a fuzzy decision model to select operating systems for firms, while actually taking into consideration the subjective judgments of decision makers. They chose certain criteria, C1 through C7, which included security, protection, memory management, software features, and others. And they actually organized the criteria in a hierarchy where, as we can see, we have criteria, sub-criteria, and if needed, also sub-sub-criteria. So to determine the weights of these criteria, the authors actually elected to use fuzzy AHP as opposed to regular AHP, since they wanted to include and account for the uncertain judgment of decision makers and the human thinking style, which AHP, the traditional method, actually does not account for. Thus, they elected to use fuzzy AHP. After that, after we reached these weights, we wanted to actually rank these operating systems based on these weights. So the authors used Topsys method, and eventually they computed this value, which helped them to rank these operating systems. Our second case study is concerned with web service selection, which is actually a tricky task to do, Since we have a lot of web services offered and they all offer similar functionalities, thus MCDM methods are used to distinguish between these web services and to choose the optimal web service. The paper we're concerned with is towards an efficient and a more accurate web service selection using MCDM methods. The author started off with a pool of QoS criteria which were chosen by the user. We had web services, and to eliminate the dominated web services, the authors used the skyline method to end up with a pool of non-dominated web services. To determine the weight of the chosen criteria, the authors used a BWM, or best-worst method, to determine these weights. Next, we have to rank these web services according to the weights we calculated. Thus, the authors elected to use 4 different methods to determine this ranking. These methods were Vickers, SAW, Topsys, which we discussed earlier, and Corpus. Actually, each method ended up with a slightly different ranking than the other method. And to actually determine which is the optimal, the authors used the Borda voting method to reach the compromise solution and to evaluate the accuracy of each method to determine which had the most optimal ranking.